Hello everyone, welcome to the Electron Flow Academy. So our today's topic is AC through RL circuit. Okay, so the resistance and the inductance are connected in the series format here. Okay, so let us consider a voltage which is the V applied across the circuit consisting of resistance R. This is our resistance R and the inductance which value is in XL connected in series. Okay, so when the voltage is applied, the net current which is flowing here starts flowing. So when the current I passes through a resistor, this resistor, it causes a voltage drop of IR. Okay, with, or we can say that the in phase with the current. So we can write the voltage drop across the resistance. So V of R is equal to I times of R. Okay. Next thing is that since it is a series circuit, current phasor is taken as a reference. Okay. So if I draw the phasor diagram, okay, the phasor diagram will look like this 0 point. This is our phasor of ampere. Okay. This is current and V of R is equal to I times R. So this is the phasor diagram of the drop across resistor. So we can, in other words, we can say that the phase angle difference while the current is flowing through the pure resistive is 0. Okay, 0 degree. And if I talk about the voltage drop across the inductance, the phasor diagram will look like this. This is our current and this is our voltage, which is VL. So we can say that the current is leading by 90 degree. Okay. So leading I by 90 degree. Okay. So voltage is leading by. So this is in the case of the pure inductance. Okay. So the voltage drop across the inductor is given by the V of L is given by I times XL. Okay. So we have the two elements here. Those are connected in series. So here, if I talk as per the KVL, so according to the KVL, according to Kirchhoff's voltage law, the applied voltage V is equal to the phasor sum of the VR plus VL. Okay. So V is equal to VR plus VL. Okay. But the voltage drop VL is 90 degree ahead of the VR. Here, the voltage drop VL is 90 degree. We can see here in this case. Okay. Ahead of the VR. So therefore, the operator J is used to denote this lead. So here we have to write the equation like VR plus J of VL. Okay. So we have to use this operator, J operator. Okay. In other words, we can see this iota. Okay. So here we have the equation. This is our equation number 1. So the phasor diagram of this equation. Okay. So the phasor diagram of this equation is looks like in two format. The first format is of voltage triangle. If I draw the voltage triangle of this equation, equation number 1, it will look like this. 1 minute. This is our point 0. This is our voltage VR. In the case of the resistance, the current is in phase with the voltage. Okay. And from the VR, the 90-degree apart is VL. So this is 90-degree apart our voltage, which is J of VL. Okay. Which is J of VL. J of VL. Okay. This is our amperes. And the total voltage is the resultant of the both. So the angle of the resultant is, we are assuming here phi. So this is known as the voltage triangle. Okay. And the another format is, second one is impedance triangle. So impedance triangle. So impedance triangle will look like, impedance triangle will look like this. This is our x-axis, resistance, and this is our J of XL. Okay. So the resultant is total impedance Z. So the angle is of, at an angle of phi. So this is the impedance triangle. Okay. So from the phasor diagram, it may be observed that in the series RL circuit, current lags the applied voltage by an angle of phi. Okay. By an angle of phi. So here, in the case of in RL series circuit, current lags, current lags voltage by angle phi. Okay. So basically this angle phi, this angle phi is nothing but the power factor. Okay. This is nothing but the power factor. Okay. So from this triangle, we can write, from that triangle, we can write that the tan of phi is equal to VL divided by VR, or phi is equal to tan inverse VL divided by VR. Okay. So from that equation number one, this is our equation number one. Okay. So we may get that now the voltage is equal to I of R plus J of I XL. Okay. J of I XL. So here we can write that expression like V upon I is equal to R plus J of XL. Okay. Now here it is clear that the ratio of the applied voltage to the resultant current, this ratio, okay, which is V upon I, is called impedance. Okay. So this is the ratio which is called the impedance of the circuit, and it is denoted by, capital Z. Okay. So the impedance may be regarded as a combined opposition offered to the flow of AC current. So basically the equation of the impedance is equal to R plus J of XL in the case of the series connection of resistance and inductance. Okay. So since the Z is equal to V upon I, okay, or R is equal to VR upon I and X of L is equal to VL upon I. An impedance triangle can be drawn similar to the voltage triangle. Okay, so this is our the voltage triangle. Okay, next. Okay, the angle between the impedance line and the resistance line is the power factor, which we have discussed here. The okay impedance line and the resistance line. So we can rewrite that the tan of phi equal to XL upon R. Okay, from this impedance triangle. Next, we have to calculate here power triangle. Okay, so power and power triangle. Okay, so here we have seen that in the series RL circuit, the current I lags the applied voltage by an angle of phi. So therefore, we take voltage as a reference. Okay, so here capital V is reference, and we may write the equation of instantaneous voltage and current like Vm voltage is equal to Vm sin omega t and current is equal to now Im sin omega t minus phi. Okay, because the voltage leads the current by an angle of phi in the case of the pure resistance which is connected with in series with pure inductance. Okay, so here we know that maximum value of the current is equal to maximum value of the voltage divided by impedance, and phi is equal to tan of inverse divided by XL divided by R. Okay, from this equation. So instantaneous power P is equal to V times I. Okay, so here I am putting the values of the voltage and current equation from here. So my equation will look like VMIM sin omega t into sin omega t minus phi. Okay, so total power is equal to now VMIM divided by 2 multiplied by 2 sin omega t into sin omega t minus phi. Okay, what we have done here, we have multiplied by the 2 this equation and also divided by the 2. Okay, so now our equation will look like power is equal to VMIM divided by 2 into cos phi minus VMIM divided by 2 cos 2 omega t minus phi. Okay, so this is our the equation for the instantaneous power. So now what we have to do here, we have to calculate the average power. Okay, so here average power over a cycle is given by power is equal to 1 upon periodicity, which is 2 from 0 to 2 pi. Okay. P d omega t. Okay. So here we need to put these the value of the power here in this equation. So 1 upon 2 pi, this is 2 pi. Okay. Now 0 to 2 pi Vm by root 2 into Im by root 2 cos phi d omega t. Okay. Minus again 1 upon 2 pi 0 to 2 pi Vm divided by 2 cos 2 omega t minus phi d omega t. Okay. So after solve this equation, I will get the value of Vm by root 2 into Im by root 2. Okay. Cos phi. That's it. This whole expression is will be equal to 0. Okay. So from here I get the power is equal to, we can see that this is the maximum value divided by root 2, that means which is equal to the RMS value. So RMS value of the voltage and the RMS value of the current multiplied with the cos of phi. Okay, cos of phi. So basically this is the equation for the average power in the case of the RL circuit. So this equation shows that for a given value of the voltage and current, power consumed by a circuit depend upon the cos phi. Okay, the whole power is depend upon the cos phi. So therefore, cos phi is called the power factor. So cos of pi is nothing but the power factor. Okay, and the angle phi here, the angle phi is called the power factor angle of the circuit. Okay, so this is how in the case of the pure resistance which is connected in series with the pure inductance, or we can say that the series RL circuit can be explained in this way. Okay, so thank you very much. Kindly like and subscribe our channel.